All right, conservation of momentum, really quick. Now, we've already talked about impulse and momentum and the relationship there between, we actually looked at, the forces involved with the change in momentum. So, oh no, I got to sneeze. Excuse me. I hate it when I do this when I'm trying to record. Sorry. Thank you. All right, so we know momentum then is the product of an object's mass and velocity. Impulse, we are looking at the force, and we did this Monday in lab. We are looking at the force applied through a time interval. Okay, so the amount of force through a time interval. In other words, we are actually looking at what? The rate of changing momentum. Okay? And so force comes into play there. Remember how we derived Newton's laws? We actually derived them from momentum, or he did. And so we've already looked at these, looked at linear momentum. Now linear, don't forget that's linear momentum too. I didn't stress that the other day. But we're not looking at angular momentum. We'll try to look at that next week. But linear momentum is a product of the mass and the velocity. Impulse, again, is momentum, but we are looking at the rate of changing momentum like we did in lab. And I haven't looked at labs yet, but I think most everybody's results came out pretty close. If you had a low percent difference, you were okay, and I think most all of y'all did. You had a pretty good 3 and 4% difference, so y'all did fairly well on that, and I think most all of you did on at least 2 or 3 of your runs, okay? Now, so conservation of momentum, it's just like everything else, conservation of mass, conservation of energy. The same applies. If energy is conserved, then so is momentum. And momentum and energy are related to each other because remember, when we looked at kinetic energy, it's 1/2 mv squared. Well, momentum is the product of an object's mass and velocity. So here we see both of these deal with the vector of quantity of velocity. Of course, we know that energy is a scalar quantity, work is a scalar quantity, but still we're dealing with velocities here. And so there's a relationship between kinetic energy and momentum. And when you get on into engineering school, you'll look at a lot of problems this way. You'll take kinetic energy and you'll solve your problems either from an energy standpoint or a momentum standpoint because of the relationship here, and it makes it a lot easier to work out. So basically what does it say? Well, that momentum is conserved. So how would we write that equation? There's a couple of different ways you can write it. You can say that P initial is equal to P final. You can write it that way. Or we can say that the if we say P initial plus P final should be equal to 0. In other words, the sum of the momentums should be equal to 0. Okay, so we can write it either way. And I think we have a slide coming up where it shows us these equations. All right. Now, so if we have, and here they show 2 skaters touching or colliding. I don't know that they're necessarily colliding, but they do touch. We see that if they push off of each other, they're moving in opposite directions, and when they touch or push, well, the velocity of A transfers to the velocity of B, and the velocity of B, in a sense, will transfer to the velocity of A. It's just kind of a flip-flop here. And this coincides with, if you think about it, Newton's third law, where we have forces act in pairs, equal and opposite, okay? All right, now, and again, they're just emphasizing here again that that they are vector quantities. Nothing has changed there. Nothing has changed there. Now, what about elastic and inelastic collisions? Now, one thing I do want you to remember here is that in an elastic collision, The total kinetic energy, of course, now, folks, momentum is always going to be conserved. Momentum is conserved. You need to remember this now. Momentum is conserved in an elastic collision, all right? Something else, too, is conserved, total kinetic energy. So whatever the energy of A is and B is, it should be the same after the collision. In other words, there's no loss of energy, okay? Now, it's very important you understand elastic collisions. Now, elastic collisions, how do we know if it's an elastic collision? Well, they bounce apart. Well, they don't always bounce and go into opposite directions. And if I have time, I may not get to it today, but maybe Monday, I'll pull up a PhET simulation, and you can actually have an elastic collision and they move in the same direction, okay? It can be totally elastic, but yet both objects, when they collide, they move off in the same direction, okay? So, you know, they don't always hit and bounce apart, okay? Not always, all right? Because what if one object's sitting still, okay? If object B is not moving, okay, well then that makes a difference when they collide, okay? So they don't always hit and bounce apart, but typically we understand that when we do see objects hit and bounce apart, that's an elastic collision, okay? But the key thing to remember, what makes it elastic, it's not that they bounce apart, it's that momentum's conserved and total kinetic energy is conserved, okay? That's what makes it elastic. All right. So if we do the calculations and we see the energy before and after is the same, then we know it's elastic. If we do the calculations and see that it's different, then it's inelastic. For example, car crashes. What do you think a car crash would be? You know, if someone hits and okay. Would that be elastic or inelastic? They stay in contact. So it's really more inelastic, okay? Now, we can't just sit here and say that all car collisions are totally inelastic, because there is a little bit of elastic there too. So they're a little bit of both, but they're more on the inelastic side in that there is energy loss. Now, where does the energy loss go? Well, a little bit. All right, have you ever seen a car after a wreck? It's crumpled, isn't it? So the energy lost goes into the deformation of the vehicle. Does that make sense? Yeah, that's what causes the vehicle to crumple up, okay? Okay. And you want that, or you want something to absorb that, because there again, that's going, you know, the old cars, you know, back in the 20s and 30s, man, they were built out of steel. They were sheet metal. My dad witnessed a car accident one time when he was about 18 or 19, right here in downtown Boaz. The little old building here, it used to be 4-Star Printing at the red light that they're now taking down, right there on the corner. It used to be 4-Star Printing before they moved right behind it. It was actually a little restaurant. It was called the College Inn. And my dad worked there. He fried hamburgers and stuff and served ice cream and stuff. And he said there was a bad car accident right there one night. And he said like a 30, I think it was like a 35 Ford had a head-on collision with like a 49 Plymouth or something like that, or 47 Plymouth. And he said that Ford the front end of that Ford just went about halfway up into the front end of that Plymouth and didn't even hardly hurt the Ford and just destroyed that Plymouth. And there was that much difference in just that short span of time and how much they, you know, how rigid they built the cars over that short period of time from 30s to 40s. They had really weakened them a lot. They had, you know, they'd made the metal a lot thinner and they had weakened them a lot. So he said, I was just amazed at how it didn't hurt the Ford and it just destroyed that Plymouth. So I think it was Plymouth. So you see the crinkling and crumpling of the car, a lot of that energy loss goes there, okay? So that's inelastic, all right? And typically we say inelastic sticks, like you said, it sticks. They stick, okay? All right. Okay. But the key thing is that there's a loss of kinetic energy, okay, in inelastic, all right? So that's elastic. Now, I don't think they define, and I don't know why they don't, so let's remember that. Okay, and again, that's just yeah, here it is. Yeah, I thought it was in here. All right. So an inelastic collision, then what? Again, momentum is always going to be conserved, y'all. Momentum is conserved, all right? Momentum is conserved. However, the total kinetic energy after the collision is less than before the collision. All right? So please remember that. Notice they put Velcro here, and now the Velcro is going to make it stick. Okay? So the energy before or the energy after is less than before. And that's what makes it inelastic. Okay? And so car collisions are a combination of both. They're more on the inelastic side than the elastic side, but there's no such thing, and I have to be careful saying this, there are occasions where you have pure, truly elastic and inelastic, but most of the time collisions are a little bit of both. You're not ever going to have every collision that's perfectly elastic or perfectly inelastic. They're a little bit of both, okay? So, but we can study them that way. We can say, okay, let's make it inelastic and let's make it elastic for the purposes of understanding the differences in the two, okay? All right. Okay, again, just the same thing. All right, they stick together. Notice they said they stick together, okay? So they stick together. Now, notice when they stick together, it is called completely inelastic. So if they do stick together, completely, then we can call it completely inelastic or perfectly inelastic is another way we can say that, okay? So we can call this perfectly inelastic, perfectly. Now, you don't have to write every single thing. It's kind of, the rest of this stuff is just kind of regurgitating the same thing we've already said. But perfectly inelastic, they will stick together, okay? All right, let's move on. All right, now, and here we see the car crash. Hey, that might be my dad there. No, that's not my dad. All right. Well, that's an old car, you can tell. All right. Okay. Okay. Notice the absorbed energy can't be recovered, okay? Again, talking about the collision, and that's why we say it's lost, okay? Because you can't, how are you going to get that energy out of that crumpled up car? Well, you're not, okay? Well, that's a wreck, isn't it? Okay. All right, elastic collisions. Billiards is a good example. Is probably the closest thing we can think about is to having a perfectly elastic collision, shooting pool. Okay, that's probably the closest thing to a perfect elastic collision, shooting pool. Now let's look at some equations. Okay, now I thought about going into the derivation, but goodness gracious, forevermore, we'll be here about 10 or 15 minutes deriving these equations, and I don't want to spend all that much deriving them. If you look on page, I'll just say this much, because I'm not going to make you derive them. There's no sense in making you derive them, just as long as you know where they come from, okay? Because we get into the difference of squares and everything. But if you look on page 251, how did we come to these equations right here? Now, what are the two equations? All right, notice right here, how do we find the final velocity of A and the final velocity of B? Okay, if you look on page 251, notice we start with kinetic energy and momentum. And we take those two equations and we actually divide one by the other and then come back around and substitute. And when we substitute in to this equation right here, okay, we come to this equation and this equation. Again, if you'll take your kinetic energy equation 8, I'm not going to write it all down, 8.19, and then your momentum 8.20, and set those up and then divide the kinetic energy by the momentum, you'll notice there'll be a difference of squares in there. And then you take equation 8.23 and substitute it back in, you come to these equations here, okay? And it's a very long, drawn-out process of solving these equations. Now, please understand, these equations are for one body at rest before the collision. So when you write these down, when you write these two equations down, now, do you understand that this is for body A, the velocity of body A final? I don't know why they put 2. I wish they'd have put F. and this is the velocity of B final. Notice how on both of these, we use the initial velocity of A on both of these. Okay, well, why? Well, we can't use the initial velocity of B because the initial velocity of B is 0. That's exactly right. So these equations are only when the initial velocity of B is 0. Okay. If the initial velocity of B is not 0, then we have to solve different equations, okay? But we're just going to stick with this right now. We're just going to do this, all right? A little bit more complex equations, okay? All right. Now, so those are for when it is only when B is 0. Or A could be 0 and B be moving. In other words, one of them is moving, the other one's sitting still initially, okay? And it doesn't have to be B that's sitting still. It could be A, all right? And B's moving, all right? Everybody with me on that? And they throw a lot of equations at you, but again, I'm just going to focus on the main ones because I want to move on and talk about center of mass, okay? Okay? But that's elastic and inelastic. Now, how would we do an inelastic collision? How do we calculate for an inelastic collision? Okay? Well, let's look at inelastic collision equation. Let me stick a slide or two in here. All right, what would the equation be? All right, we know that momentum is going to be conserved. So P initial is equal to P final, right? All right. Okay. So in an inelastic collision, we have object A and object B. Why don't I put that plus sign in there? We've got object A and object B. All right. And let's say object A is moving this way and object B is moving that way. And they collide. And then after the collision, they stick. So after they stick. Okay? Now, which way is it going to be moving? Well, it all depends on which one has the greatest velocity. Okay? All right? So this is inelastic. Inelastic. All right? So how do we solve this problem? Okay, well, we've got the momentum of A, so we've got MVA initial plus MVB initial, initial, is equal to, they stick together, so then it becomes what? M of A plus M of B times V final, and we could call that V final of the system, of both, whatever you want to call it, okay? Whatever you want to call that, all right? But that's what your equations, now these are easy to solve. These are cake, all right? These are to me, I love working the inelastic ones because they're easy, okay? Now notice again, you can have A and B moving here, all right? So we can call that V final, or we can say V final of both. Would that make you feel better? It doesn't matter. V final, because they're stuck together, okay? And so then if we want to find V final, then we can find it. Or we could, if we knew the final and we needed to find the initial velocity of B, we could solve for it, or initial velocity of A, we could solve for it, right? So here is an equation. This is your inelastic equation. Okay? That's your inelastic equation right there. All right? So make sure you have that on your formula card. And I don't know why, I don't think the text actually shows you that. They kind of, I think they kind of assume that you can figure it out from conservation of momentum. Is it in there, or did I overlook it? I don't think it is. I don't think it is. No. No. Okay. All right. Any questions? All right. Now let's look at center of mass. Okay. Center of mass. All right. So center of mass is related to momentum. How do we define center of mass? Well, basically what we do is what we're looking at several objects, and we take the radii of these objects, or their positions, from the origin, and we want to determine where they, in other words, balance. Okay? Where they would balance, the center of mass would be. Okay? So this is a real easy equation, and this is kind of leaning a little bit towards torque. When we look at torque next week, the equations are similar because when you look at a fulcrum, a lever and a fulcrum, how much torque is produced will depend on the length of your lever and how much mass you have and how far it is from your fulcrum as to how much torque you can produce on a lever. If you've ever used a lever, let's say you've got something very heavy to lift, you've always noticed your lever arm has to be really long, doesn't it? Your lifting arm is short and your lever arm has to be really long if you want to pick up something really heavy. My daddy was a master at doing stuff like that. We moved a big old outbuilding one time. It was like a 14 by 16 metal outbuilding. Just me and him using levers and blocks. And yeah, it was heavy. It was several hundred. It was probably 1,000 pounds or more. And we just it was up about that high off the ground, but we had to move it across town. And so we had a big old trailer, and we used levers, 4x4 posts, 14 foot long, and had blocks, and we'd raise up one corner, and we just worked our way around until we got it high enough to back a trailer under it. It's real easy. It wasn't hard at all. I mean, because the lever, the length of the fulcrum, you increase your mechanical advantage. Okay, so you multiply your force, not the work. Remember, we talked about that a few weeks ago. We're multiplying force, not the amount of work. The amount of work's the same, but it's a force multiplier. So that gets into torque. So this kind of leads into torque. Okay. All right. So here's your equation right here. Look, the sum of the mass times the radius divided by the total masses. Okay. Now we can do this now that cm stands for center of mass, not centimeters. Okay. Please make a note of that. All right. All right. Please make a note of that. That's center of mass. Now, we can do this for x, and we can do it for y. It's the same equation. In other words, if you have, and we're going to do a problem here in a minute, I give you a set of coordinates. You've got three objects. Let's say object 1 is 0.1 kilograms, and it's at 0.2 and negative 0.1. Well, how do you do that? Well, you do the x and then you do the y. Okay, center of mass. All right, and I think problem 51 we're going to do, and I'll let you see how that works. Okay, but this is another way to look at how momentum is conserved. Okay, by looking at center of mass, the distance from the origin of an object. Okay, all right. And notice that the shape really doesn't affect center of mass, because center of mass is what? Center of mass, okay? It's literally where it's located, where it centers, okay? In other words, if I wanted to balance that cube, I would have to do what? I would have to find its center of mass, wouldn't I? Anybody ever balanced a knife? Okay, on their finger, or anything on their finger? It's real heavy on one end and lighter on the other. You have to find the center of mass, don't you? Okay? All right. Okay, motion of center of mass. Well, that goes back to momentum. Really don't want to look at that, okay? All right, that's where I want to stop, okay? Because that's basically momentum. Same thing. All right, let's look at some problems. No, I don't want to say that, but I do want to go to some problems. All right, because I'm going to add a couple of problems. How far did I get? What was the last number on the problems I gave y'all? 11? Okay. All right, let's add these. All right, so 11. And today, here in just a little bit, I'm going to set up your Chapter 8 quiz, and that's going to be the last quiz. No more quizzes after that. We will work we'll work a few problems in Chapter 9, but we'll just do those in class. I will take these up. I'll tell you what, next Monday, let's come to class and let's be ready to work some of these. We'll talk about which ones I might call on y'all to work, okay? All right, so number 11 was the last one I gave y'all. All right, let me just write them all down again. Make sure we got them. All right, so we said what? 1, 2, 4. All right, 1, 2, and we did all three of those, right? 4, 7, and 11. 16, 18, and 21. 33 and 36. And 47 and 51, yeah. All right, 47 and 51. That's it for Chapter 8, yeah. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12, okay. Yeah, I'll take those up next week and give them back to you and just give you a grade for them. Let's look at, I'll tell you what, just be ready to work whichever one you want to work. Put it that way. Whichever one you feel comfortable working, just be ready to work it. I'll call on a couple of you guys, maybe Monday, or, dang though, if I take them up Wednesday, y'all won't have time to get them back for the final. Yeah, I'll have to take them up Monday. Huh? Dibs on number 1. Okay, all right. Okay. All right, we've already worked 1, 2, and 4. I might actually call on one of y'all to work one that we hadn't worked. All right, let's see. Number 7. I think y'all can probably work it. Let me look at it, see what it looks like. Number 7. Yeah, number 7 is just a impulse problem. That doesn't seem that far out. Number 11, we actually have to solve for the constant and then do an integration. Okay, y'all think y'all can do that? Number 7, do you want me to give you the answer? Well, you know, you got the answer in the back of the book on number 7, number 11. Y'all want to look at one of these, or you want to look at conservation and... I'd really like to go over the conservation and... all right, let's do... All right, number 7 is easy. I'm just going to quickly... All right, number 7, all you had to do was find the average force. This is all you had to do. And it's change in momentum over the time. I'm going to just kind of get you started, and then we're going to move on. And you don't forget now, change in momentum is mv final minus, you did this in lab, mv initial over delta t, okay? And the time interval was really short. Yes, 2 milliseconds, that's 2 times 10 to the negative 3 seconds, or 0.002 seconds, okay? You should have gotten 562.5 newtons when you work it out, okay? So that's the equation. Again, that comes from your impulse equation.
How many seconds you said it was?
That was 2 milliseconds. The time is 2 milliseconds. That is this. That is 0.002 seconds, okay? Or 2 times 10 to the negative 3.
On that MV, F minus VI, is that...
Change in momentum. Mm-hmm. That's delta P.
Okay.
Yeah, that's delta P broken down. Yeah. Remember, delta means changing it. Final minus initial. Mm-hmm. And that comes from this equation. That comes from delta P is equal to the force times the change in time, your impulse equation. That's where that comes from. okay? Because remember, y'all, change in momentum, which is the same thing as this right here, okay? Which is the same thing as this right here, okay? Remember, y'all, we did this in lab. Remember, changing momentum is impulse, which is force times time. All right? Don't forget that. Okay? All right, any questions on that? Let's look at number 11. You want to do number 11? See if y'all can do number 11. That's an integration. Let me give you a hint, and I'll walk around and help you. Number 11, you got to find a, notice it gives you, do I need to pull a book up? I always forget. Y'all don't have the book. All right, let's do this. Let me pause a second. Seven what? B would be what? And that's what? So that's 500 newtons second squared times what? 3.5 cubed over 3 minus 500 newtons second squared over 2 cubed over 3. And J should be 5812.5 kilograms meters per second. Now wait a minute, I know some of y'all are saying, now wait, where'd you get that kilograms meters per second? Shouldn't it be newtons? Because that's seconds. Shouldn't it be newton seconds? Okay, y'all, newton seconds will reduce to kilograms meters per second. Right? I did that the other day in class. I showed you that, okay? So newton seconds is the same as kilograms meters per second. Everybody get 5812.5? Okay, good. All right, now what about part C? Part C said what? By how much does the rocket's velocity change during the time interval? Assume constant mass. Okay? All right, well, how do we find that? How would we find that? All right, we know this, don't we? It started at time 0, right? So what's the initial velocity? 0. All right? So right? That term is gone. Right? So now it's just what? V final is equal to what? Impulse over M. So 5812.5 kilograms meters per second divided by, was it 2150? That was the mass of the aircraft, rocket. Now you see why I like to leave it kilograms meters per second? All right. Let's not lose our head, okay? When we're doing these problems, don't forget what everything represents. Don't forget that momentum, y'all, has velocity in it. It's a product of an object's mass and velocity. Okay, so don't forget that. And we were dealing with impulse, so we know that impulse is changing momentum, and if we start at time 0, the initial velocity is 0. Okay? And we get an answer of what? Yeah, 2.7. Very good. All right. That's a good test problem right there. I like that problem. Some of these problems, most of these problems in the end of the chapter, they're good. They're good problems. There's a few here and there I don't know. I don't like the way they're worded. But that's a good one. All right. As a whole, I like this book better than any one I've ever used. It's a good book. Okay. All right. Let's look at the conservation of momentum problems. Okay. 16, 18, and 21 are all very similar. Um, um, yeah. Okay. You want to look at 21? Yeah, 21. Yeah. Oh, no, I'm sorry. 16. Oh, yeah, I got to pull it up so y'all can read it. So number 16 is negative 0.105. All right, let's find one a little more interesting. We're actually out of time, though. Okay, I'll tell you what.